Good evening, Yes Prep. It's me, Mr. DeRosier, here at Yes Prep East End. And what I have is the first installment of the calculus review videos for this year. We're coming up on our first unit exam. This unit exam is going to cover everything we have learned about limits, everything we've learned about continuity, horizontal and vertical asymptotes, the intermediate value theorem, and depending on the school that you're at, there's also going to be some questions on the derivative and what that really means for us, as well as what it's going to tell us about the function. Unlike some of the previous videos I've done where I'm standing up here and I'm going to be writing on the screen, I'm actually going to use the document camera. So you're not going to see much of me over the course of the next hour. Might be a good thing, might be a bad thing. But what you will see is you'll see me writing up here on the screen. From time to time, I'm going to jump in and I'll review the hand motions, the sort of power teaching that goes along with some of the different concepts. For my kids at East End and my kids from Southwest, you've done all of these hand motions with me. If you're at North Central or Southeast, may or may not have happened, so feel free to skip past those. But I've definitely found that when I'm doing the hand motions, when I'm doing the power teaching, it helps make some of these ideas really stick with the students, and it helps them as they're applying the templates moving forward. So with all that said, let's give it a shot. The key ideas that we've come across in this unit is what is a limit and how do you go about finding it. Several different methods for doing that. We're going to go through many of those. When does a limit fail to exist? How do you actually write and convey to a reader that you know the limit exists and you know the why? As I mentioned earlier, the different techniques for finding limits. We're going to come back to our friends, the horizontal and vertical asymptotes that we've studied in Algebra 2 and again in pre-calculus, and we're going to apply now our AP Calculus understanding of why asymptotes exist in some functions. We're going to talk about how do you convince a reader that a function is indeed continuous at a point. We'll talk through the intermediate value theorem. That's the one I keep referring to as the common sense theorem. And then we're going to talk about finding the slope of the tangent line to a curve. And then finally, we'll talk about what does the slope of that tangent line tell you about the function. I estimate this is going to be about a 1 hour long video. We'll see. So, get yourself a snack, get a beverage, sit down, and let's enjoy some good calculus learning. Okay, let's start the conversation with what is a limit and how do you go about finding it. As we discussed last year in pre-calculus, there is a difference between asking what is the value of a function, which is what I'm asking here, what is f of 3? F of 3 means if my x-coordinate is equal to positive 3, and I go over to the function, what's the y value? Well, I don't know if you can see it, but up here on the graph, there is a hole at x equals 3. So the function is not defined to be at that point. It's actually down here. There is this point located at 3, negative 2. So the value of our function is going to be negative 2. That is different. That is fundamentally different from this question. With a limit, the way we're going to read this is what's the limit as x approaches 3 from the left of f of x. What that means graphically is as my x values get closer and closer and closer and closer to 3 from the left-hand side, what are we seeing on the graph? What are we seeing with the y values? Well, as I get closer to 3 from the left-hand side, the function is increasing towards this hole. The hole is actually located at the coordinates 3, 3. So as the x values increase towards 3, the y values are increasing towards 3. And we would say then that the limit as x approaches 3 from the left is equal to positive 3. The limit as x approaches 3 from the right, we're going to get closer and closer and closer to x equals positive 3. We're coming in from the right. What's the behavior that we see happening with the y values? They are decreasing towards the hole. They are getting closer and closer and closer to this point 3, 3. So the limit as x approaches 3 from the right is positive 3. Now we get down here to the question, what's the limit as x approaches 3 of f of x? When there is no sign indicated after the number, we take that to mean you're approaching it from both sides. And so this is where my kids at East End and Southwest, we've done the power teaching that goes like this. In order for a limit to exist, the limit from the left and the limit from the right must be equal to each other, and a hole in the graph is okay. So the limit from the left, in this case, is positive 3. The limit from the right is positive 3. Those are equal to each other, and even though there is a hole in the graph, we would say that the limit is equal to positive 3. If I go down to this fifth one, I now have the limit as x approaches 0 with the plus sign. Limit as x approaches 0 from the right. As I get closer and closer and closer and closer to 0 from the right-hand side, if I pay attention to the function is decreasing, and it looks as though it continues to decrease off of the page. So as we get closer to 0 from the right, I would say in this case that the limit is equal to negative infinity. Review of some vocabulary that's going to be coming up in a little bit. Because as we get closer to 0 from the right, the graph continues to decrease, we would say that this graph has a vertical asymptote at x equals 0. It also seems to me that the graph is flattening out as we head off to the right, so if that's happening, then we most likely have a horizontal asymptote. Since we don't know the exact equation that was used to generate this curve, we're really just speculating on those things, and we can talk more about that later. Limits exist. In order for a limit to exist, your limit from the left and the limit from the right must be equal to each other. This first case, if I were to ask you to find the limit as x approaches 0, well, I can see from the graph, as I get closer to 0 from the left-hand side, my y values, they decrease, but as I get closer and closer to 0 from the left-hand side, the y values appear to be getting closer to the origin. So the limit as x approaches 0 from the left is positive, is 0. The limit as x approaches 0 from the right of f of x, I come in from the right, the y values are decreasing towards 1. Since these limits are not equal to each other, we would say that the limit as x approaches 0 of f of x dne does not exist because the limit as x approaches 0 from the left is not equal to the limit as x approaches 0 from the right. That is one reason, that's the first reason we encountered, that functions may not have a limit that exists. The second one, let's go down to this one. This point on the graph is located at 2, 0. If I were to ask for the limit as x approaches 2 from the left of f of x, the limit as x approaches 2 from the left, y values are decreasing towards 0. But let's look at the limit as x approaches 2 from the right. If you can see the graph, we have this graph that decreases towards 2, 0, but once I pass this point, I don't have any graph defined. I don't have any points above the x-axis. I don't have any points below the x-axis. So the limit as x approaches 2 from the right doesn't exist. And I would say because of a domain restriction. Because I have nowhere to plug those numbers into. I have no points on the graph defined for larger than 2, so the limit as x approaches 2 from the right doesn't exist. Since these are not equal to each other, we would say then that the limit as x approaches 2 of f of x doesn't exist. And the same reason as before, because the limit from the left and the limit from the right are not equal to each other. This last one is sort of a new one for me this year. If you were asked to find the limit as x approaches positive infinity for f of x, meaning what happens to the graph as the x values increase forever off the screen. Well, if we pay attention to the graph, it decreases, then it increases, then it decreases, then it increases. It seems to do this behavior where we're going to continue to increase and decrease, never settling on, never getting closer to one particular number. That's called oscillation. The limit as x approaches infinity of f of x does not exist because of oscillation. O-S-C-I-L-L-A-T-I-O-N. Be careful though, because if you were asked to find the limit as x approaches 0, even though the graph oscillates as you head off towards positive infinity, if I want to know what happens as the x values approach 0, well, as I get closer and closer and closer to 0, the y values get closer to the origin, so the limit as x approaches 0 would just be 0. So to sum up, 3 reasons that a limit would not exist. In the first case, limit from the left, limit from the right are not equal to each other. In the second case, the limit from the left exists, but the limit from the right does not because we have a domain restriction. The third case is that the limit as x approaches infinity doesn't exist because of this oscillation, the wobbling factor.